Okay, so please welcome Karianne Bergen, who is an assistant professor in computer science and in data science and earth, environmental, and planetary sciences. She studies scientific machine learning with a focus on machine learning and large-scale data analysis in earth and climate science. Today, she will show how AI tools are changing what and how fast we can learn about our planet. Please join me in welcoming Karianne Bergen.
Hi, everyone. I'm not used to holding two things at once, so we'll give it a try. Okay. Let me know if you can't. Am I too far away from the mic? Can you guys hear? Okay. Right. Thanks to the organizers for inviting me. It's exciting to be a part of a conference that has such a diverse set of perspectives on AI. So today I'm going to talk about the work that I've been doing in earth sciences and some of the things that have been going on. It's a field that I've been working in for over a decade now. And so I think hopefully you'll find it interesting to learn a little bit about what we're doing in the earth sciences. So in particular, I'm going to talk about two different topics within the earth sciences. One is advances in earthquake science. This is a case where we're using AI to get better data products that are used by researchers to then draw better scientific conclusions. And then we also have machine learning and climate modeling, where we're using machine learning to basically speed up simulations and be able to get results faster and do science we may not be able to do otherwise. But before we go into that, I just want to kind of give some context for the scope of what I'm going to talk about. I'm not going to really talk about generative AI in this particular talk. I'm going to focus on what I'm going to refer to as machine learning. So machine learning, I'm going to refer to those as tools for data analysis and discovery in scientific data, things like predictive modeling with supervised learning methods, pattern discovery with unsupervised learning methods, generative and foundation models for scientific data I would put under this umbrella. I'm not going to talk about these too much. This is a topic that's kind of an emerging area, so I don't have a lot to say about it yet. And so I will mention toward the end sort of generative AI tools. I view those more as research productivity tools. And I'm going to focus more on kind of the data analysis and scientific discovery. But I will mention generative AI just briefly toward the end, sort of my thoughts about that being used in the sciences. All right. So in the earth sciences, it's a really interesting field. My background's actually in data and computational sciences, but I've been working with earth scientists for a little bit over a decade. There's a lot of interesting problems in earth sciences. It's a really interesting field of science because it sort of includes all the other sciences. People are doing biology, chemistry, physics, mathematics, computing, all within earth sciences because the earth system is complicated. There's all these different aspects to it, a range of different problems. So if you're a student looking for interesting problems, there's a lot you can do in earth sciences. It ranges from the biosphere to the solid earth, the liquid and frozen water on the earth, and our atmosphere. And there's a number of problems across the earth sciences where we're using machine learning. I can't talk about all of them in this talk, but there are some common themes I want to tell you about before I jump into sort of the two cases that I'm going to tell you about from my own research. So in the earth sciences, when it comes to sort of machine learning applications, there are some major sources of data that we often work with. One is observational data. There are Earth-observing satellites that capture hundreds of terabytes of data per day. These are sort of images of the Earth. There's also in situ sensors. So these are point instruments recording sort of a point observation in a continuous spatiotemporal field. You might have fixed stations, like we'll talk about earthquake seismology. We have fixed seismometers in that field. When we're talking about the ocean atmosphere, sometimes those sensors might be moving, like with the currents. We also, in earth sciences, often are working with proxy data. So sometimes we can't directly measure the thing we want. Those who study paleoclimate, or sort of the climate of the past, they can't directly put out a temperature sensor to measure past temperature. So they have to do things like measure isotope ratios and ice cores to get that information, which is sort of a noisy source of data. We also think of climate models when we think about earth systems models and the outputs that those produce. Those are another form of data, even though they're produced by a computer. So we'll talk about that when we talk about climate modeling. And these simulations can be quite large. You can have petabytes of data produced in some of these climate model intercomparison projects. And finally, a lot of times scientists are not working with these observational data or models directly, sometimes they're using sort of a combination of them in the form of data products. So I'll mention briefly in the talk atmospheric reanalysis data. This is where we take weather observations and sort of physical models of the atmosphere and combine those to get a snapshot of our sort of best guess of what the global weather looks like at a particular point. And then earthquake catalogs, which I'll tell you more about in the first part of the talk. And there's a range of different challenges that arise analyzing these data sets. I won't go into this. If this were like a machine learning conference, I would talk in way more detail about these, but I'll give you sort of an overview. So some of these challenges are related to the nature of the tasks and underlying processes. So we're often interested in extremes. If we're interested in natural hazards or extreme weather, we might be interested in infrequent or rare events. So that can be challenging from a data analysis standpoint. We don't have a lot of examples of those cases to learn from. Our data are often spatiotemporal. The complexity of the Earth system means our data is very high dimensional in many cases. We have to model sort of the 3D spatial components of the Earth across time. So our data sets get large. There's a lot of spatial heterogeneity. So we have to have models sometimes that are local or regional and can't be applied globally because there's differences all across the different parts of the planet, different ecosystems. And also non-stationarity, which means the climate is changing over time. Our systems are changing over time. So this is something we have to take into account with our models. And finally, for natural hazards, this isn't for every application, but with some natural hazards related applications, we may need near real-time information if we need to use it to support data-driven decision making. The data also have some interesting properties. A lot of times we're getting data from multiple sources. It might be collected at multiple resolutions or irregularly sampled. So the data can be sort of messy to bring together data from multiple sources. The data is often noisy or uncertain, might be incomplete. If we're collecting data using sensors, those sensors might have their own noise. They might break down. There can be challenges with getting nice quality data. And some of the phenomena we're interested in, like with earthquakes, may have low signal to noise. So we may just have weak signals that appear in the data. We often have data sets that are not necessarily representative. There's often temporal and geographical biases. We tend to collect data in places where there are well-funded scientists. So we have more data from some parts of the world than others. Sometimes instrument placement is biased by convenience. Like it's harder to put a sensor on the top of a mountain than it is, on the roof of MIT, right? And one of the things that we often see is we have, even in cases where we have big data sets, we have small labeled data. Other cases, we just have relatively few samples. Data can be expensive to collect. In many cases, we may be looking at rare events, so we just haven't observed many examples. And so we're often lacking in ground truth data or have few samples, which can make AI challenging. So these are kind of general challenges, but we'll see these sort of appearing in the applications that I'm going to talk about. So during my PhD, I got involved with kind of working in earth science research for the first time, looking at earthquake monitoring applications. So this is an example visualized of an earthquake catalog. This is a week of earthquakes of magnitude 2.5 and above as cataloged by the US Geological Survey. This website is actually, it is still up and running, fortunately, despite the government shutdown. So this is actually from the last week. But earthquake catalogs are a really essential data product for seismology. So seismologists want to study earthquake hazards and processes. And in order to do that, they need to know when and where earthquakes have happened. And so an earthquake catalog is a way that they can get that listing. And so earthquake catalogs need to be as complete as possible. It's easier to pick out the larger earthquakes, but smaller ones are more challenging, even though those have scientific value to scientists. In an earthquake catalog, you might get information about where the location, where the earthquake happened, when it happened, and some of the properties like its magnitude, maybe how strong the shaking was, some of the source properties. So this is information that earthquake scientists need to do better science. So we can give them better catalogs, they can do better science, better understand earthquake hazards and processes. So these catalogs are generated using data that's collected by sensors called seismometers. This is kind of an analog, what an analog one looks like. Now they're digital, they're not very interesting to look at. But they collect this data that are basically ground motion. It's the vibrations of the earth. We have three-dimensional shaking. Here we can see this is 1 day's worth of data. I've covered up part of it. But each of these rows is 30 minutes worth of data. So we have 24 hours of data here during a foreshock sequence. So there's a lot of events happening in this particular case. If we zoom in on these events, we can see that they have a sort of distinct pattern. There's an initial wave arrival called a P wave, another wave arrival called an S wave. So we have these kind of two pulses. And this is something that you can train an analyst or a grad student. As a grad student, I end up seeing a lot of these. I can pick them out pretty easily. we can train a person to pick these out, which means it's a task that's well suited to automation with AI. And so one of the things we want to do is be able to pick out these earthquake signals as a part of developing these earthquake catalogs. Again, the big earthquakes are quite easy to pick out, but there's a lot of these little signals that can be more difficult to pick out because we need to be able to distinguish them from other nuisance signals. These sensors measure any vibrations, not just vibrations from earthquakes. So anything, it could be a truck driving by might vibrate the sensor. It can be a lot of different sources. So this is a case where earthquake catalogs, they've always been sort of automated, but the algorithms were a little bit more simple. And so we want to see if we can improve upon the algorithms using AI. So we're not adding new automation, we're adding sort of better automation, better accuracy, and more higher resolution to the catalogs. So first we have to do is identify the signals that are coming from earthquakes. So that's identifying the wave arrivals and their onset times. Traditionally, this has just been done using a simple heuristic that sort of ignores most of the shape information available in the from the waveform. This is called event detection and phase picking. Then once we have a number of these events identified at different stations, we have to identify which of these waves that we're seeing are coming from the same event. So you'll see shaking from an earthquake at multiple different sensors at different locations. You might see a number of different events at one station over time, and we'll see a number of, if we look across all our stations, there's all these different events. We have to map them back and say which of these events that we're seeing are coming from the same earthquake. So that requires another algorithm. That's called phase association, that process. And then finally, once we've grouped these events together, we can try to locate and characterize the earthquake source. So this is kind of the standard processing. And over the last sort of few years, which I'll sort of outline, we've seen these processes being replaced by AI solutions from the sort of heuristics. These two were usually done using kind of very simple physics-based physical models that are sort of optimized, like solving sort of simple inverse problems. All right, so our goal with this research was to start building, updating these kind of catalog building components using data-driven methods in AI. And during my PhD, I worked on a method called FAST, which was took a large-scale data mining approach. So we were doing an unsupervised approach that didn't require labeled data. We were doing sort of pattern mining, trying to find repeating signals. Since earthquakes, they often repeat. I won't go into all the details of that. So we're searching for these kind of repeating earthquake patterns in the data to detect previously undetected small earthquake signals. This is in 2015. That's the same year that like TensorFlow was released. So this is kind of early in to get on the sort of machine learning kind of train, I guess. A couple years later, we started to see groups using deep learning methods for this. So first, just a simple convolutional neural network, then a little bit more advanced convolutional neural network, a UNet architecture, and then a year later, a transformer, which is a method, architecture designed for sequential data. So we see this sort of adoption of machine learning happening over the span of a couple of years. So during that period, there's a lot of research on these tools, and what we're seeing now in the last couple of years is that these have been widely adopted by scientists in this field. So if you look in the literature now from the last few years, these are all papers from that I'm going to show you from 2023 to 2025. A lot of them are using machine learning-based catalogs to do their science. So for example, here's a number of these different articles, and they'll say things like new insights revealed by deep learning-based catalog. This is a really popular title for people's academic papers. It's very flashy, but it's convenient for me to find you these examples. So these are now common to see in the literature in this field. And so if we look at the sort of timeline, it took about 5 years to go from people starting to introduce these new deep learning techniques to them being pretty widely adopted and accepted by scientists in this field and actually using them in their science as kind of a standard method for analyzing data. So when we think about how fast automation will happen in the sciences, I think it varies quite a bit by the specific problem and domain. But I think for this particular problem, we can kind of see a timeline. So this is from Web of Science, just looking at sort of papers and their trajectory. This is going back 20 years. We can see that for a while there was kind of a slight increase, but it was a pretty low level of publications on machine learning and geophysics and seismology. Then around 2018, we see this kind of rapid increase. And now we've it's hard to see if we're still going up or if we've flattened off, but now we see this kind of sustained high rate of publications. I think a lot of that is coming from people using these deep learning-based catalogs to do their research. So it's become sort of standard. These catalogs often will have like an order of magnitude more events, which corresponds to sort of one earthquake magnitude higher resolution. All right. And so I think when you have a specific task that lends itself to this sort of automation, and you have the right pieces in place, which I'll say what I mean by that in a minute, I think you sort of can see this sort of timeline within a few years, this sort of 5-year time frame of the field kind of completely changing how they develop their data products and how they're analyzing their data. But this sort of inflection point here around 2018 roughly, I think the sort of rapid adoption didn't happen by accident. There were a lot of factors that were kind of happening behind the scenes, and a lot of effort put into lowering the barriers to machine learning use in this field. So I was doing my PhD during the, sort of this set of years, right before this took off. And at the end of my PhD, because of all these barriers, I was quite frustrated. So with some of my senior colleagues, I wrote this review paper, which was really meant to be like a perspective piece. I only really cared about writing the discussion part, which was outlining some of the barriers to machine learning adoption in this field. And at the same time, members of this kind of machine learning and seismology community were actively working to reduce those barriers, which is why we saw this kind of research take off. So some of those barriers were that there weren't really good data sets out there for training. Every paper, when people propose a new algorithm for catalog building, they would have to like take these, archives of data, pick out the earthquakes that were in the catalogs, make their own training set or their own data set. They'd be benchmarking their own, measuring their own performance. They wouldn't share their code, so you couldn't compare to other people. Everyone was working with their own data, their own code, their own metrics, and so it was very hard to make progress because we didn't know whose method was working well, what the relative advantages of different approaches were, and you couldn't really rerun other people's work and build on it. So that was a big challenge. There was also a need for people who had sort of both skill sets. Domain knowledge in this case is really important to have, as well as those machine learning skills. But that was an area that where there still wasn't a lot of people with both of those backgrounds. And then there's also sort of different analysis needs of scientists because of the properties of our data, which I mentioned, that often are different from the priorities of the sort of computer science and tech industry that's often driving the research. So those were some of those needs that we identified. And actually, during this period, we saw a lot of progress sort of at this time. So one was this move towards making benchmarks. So when we published our FAST method, we posted it on GitHub. At the time, that was like sort of unheard of to share your code on GitHub within that field. And a number of groups started to create large benchmark data sets that they could share, that other people could train models on. There's now toolboxes that bring together data and models. And it became sort of standard for when people were creating a machine learning algorithm to also publish their data set and make it easy for other people to use, as well as their machine learning models so that others in the community could adopt them without having to be sort of experts on these tools. So this was all sort of happening at the same time as this development. This sort of, I think, nicely ties in with Frank's talk about kind of open science, because that was really critical for this particular field. I think this kind of adoption and embrace of open science practices. There was also a challenge in getting this work disseminated. It was kind of a longstanding policy that earth science journals wouldn't allow you to publish a paper if you had released the paper as a preprint. And so that was something that we had to kind of push back on journals about. There's also a number of additional venues or new journals that were created during this time that would allow publication of research at the intersection of machine learning and geosciences, since the research is often kind of outside of what is traditionally published in each field and could be hard to publish. And finally, there's been a lot of work in terms of education and training, these interdisciplinary students, things like workshops and tutorials, and integrating more machine learning into the science curriculum. At Brown, in the earth science department, I teach 2 courses. One is to introduce earth science students to introductory machine learning and data analysis, but I also have a course that teaches computer science students kind of some of these climate applications that they can work on. So this is something that, again, also started to kind of take off during that time. I have some other takeaways, but I'm going to hold off on those because I want to kind of tie it together with my second application, which is I worked on earthquake seismology. That was fun for a while. Then I moved to Brown as an assistant professor, and I got into climate applications. So I want to tell you a little about what's going on in climate because it's a little bit different focus, but I think there's some kind of shared lessons in these 2 communities. So this is an application of building machine learning emulators for climate models. So I think model is one of these like most overused term in the sciences. Everyone means something different by it. So when I say climate models, what I mean is a computational simulation of the different biological, chemical, and physical processes in the Earth system. We're basically making sort of a like a digital copy of the Earth and able to run forward simulations of future climate. And so we have to discretize the Earth. We have equations, usually partial differential equations that govern sort of the different physical processes, and we solve this on a computer numerically. So this is kind of how a lot of the climate modeling has been done. These models are very large in terms of the amount of data they produce. If we think about even a coarse resolution climate model that's a 1 degree model or about 100 by 100 kilometer grid spacing, for each variable, for each vertical level, we'll have 65,000 variables just for a single time step. So these data sets get very large very quickly. If we have a higher resolution model, if we have a lot of variables, a lot of vertical levels, a lot of time steps, this gets very, very large. And so there's a lot of interest, because climate models, it takes a long time to run, in seeing how we can use machine learning to enhance climate modeling, making them more accurate, more fast. And we need climate models in this field because we only have sort of n equals 1 Earth. It's hard to run experiments in the real world. We have to run them on the computer, right, to sort of project different futures, like with different emission scenarios, for example. So modeling is particularly important in climate, since we can't just sort of wait for climate to change and see what happens. If we want to run those experiments, we have to do it computationally. So one of the areas where we've seen a lot of interest in machine learning in this field is in building what are called machine learning emulators or surrogate models. And an emulator is a simplified model that approximates another computational model, algorithm, or process, like an approximation of a computationally expensive physics-based simulation. In this case, we're interested in building emulators for climate models. So if we have a climate model, we might give it some inputs, forcing agents. There may be a number of different sort of Earth systems processes that we're modeling using our equations derived from our sort of scientific knowledge. We do the calculations on the supercomputer, we get our output. What we want to do with emulators is sort of treat all of these calculations as a black box and see if we can build a model that approximates everything that's happening here with a simplified model, something like a statistical model or machine learning model. So we take our previous model runs where we have the inputs and outputs that we got and treat those as training data for a machine learning model. The idea here is that we can get a simplified model that we can run on a more modest hardware like a laptop, and we can run it much faster so we can do experiments and sort of exploration that we wouldn't be able to do with the actual simulations themselves because it would be computationally prohibitive. So this is sort of enabling us to do different science that we would be unable to do because of a computational bottleneck. So we're trying to remove this computational bottleneck by having a sort of fast, approximate, sort of virtual climate model that we're calling an emulator. And emulators are being used widely in both weather and climate modeling. I've listed here kind of 4 examples. I'm only going to go through 2 in a little bit more detail, but I want to mention one is this idea of building hybrid physics machine learning models. So this is a case where you keep the climate model in place, but you use machine learning to try to predict what's happening with processes that are smaller than a single grid box. So we have to be able to tell them, the climate model, how these sort of small scale processes are impacting the overall climate, so they can represent them in the climate model. And there's interest in using machine learning to improve those approximations. So it's sort of using it to model very small scale processes that are smaller than a single climate grid box. This might be something like clouds. Clouds are a climate model, grid box is 100 by 100 kilometers. Clouds are much smaller than that, right? So if you want to include clouds in a climate model, you would have to pass that information to the climate model through what's called a parameterization, and we can try to improve those using machine learning. There's also interested in kind of mapping between different scales of model resolutions. This is called statistical downscaling in the climate community, but basically mapping what you might get from a coarse resolution climate model to a higher resolution regional scale model and learning to do that mapping with machine learning. I have a paper with a student on this topic, so I'm happy to send it to anyone who's interested. But I want to talk about 2 applications in a little bit more detail. One is machine learning weather forecasting emulators. These have gotten a lot of kind of hype in the media, and I think have some parallels with what we saw with the seismology case. And then I'll talk about my group's work with the machine learning emulators for ice sheet models. So emulators are often used for kind of climate models or modeling kind of subsystems within the Earth system, which is what we're doing. Okay, so these machine learning emulators for weather forecasting, what they do is they take in sort of an initial state of the weather, And then they predict the next date. And you can feed that back into the model and sort of roll out a forecast for up to, say, 2 weeks. That 2 weeks is roughly how long you can forecast the weather. This is images from GraphCast, which is DeepMind's model. There's a number of these different models. Most of them are coming out of industry. So we have GraphCast, Forecast Nets developed by NVIDIA. There's also the European Center for Medium Range Weather Forecasting, which is one of the leading weather forecasting agencies, has also developed an AI system. So that's kind of an example of a non-government model. But they're sort of kind of following these other methods or these other models. And this is, I think, one of the reasons that we've seen a lot of success is because this is a very data-rich application. This has been trained on reanalysis data. So because weather happens all the time, every day, every hour, we have a lot of data for this application. And so having a lot of data has really driven a lot of the progress that we've seen, as opposed to the architectures. Like, these models are all different architectures, but they get roughly the same results. It's really having a high-quality data set that's been helpful in seeing these results. And the advantage here is that we're able to now run these, make weather predictions about 10,000 times faster than you would with a traditional numerical weather prediction model or numerical weather prediction system, which enables you to do rapid ensembles, to study things like extreme events in a way that you wouldn't be able to if you just had the original numerical weather prediction systems. This is an area of active research. So right now these models are purely data-driven. They don't really have physics built into them. The physics is all coming from the data, which means there's sort of questions about how well they generalize. Physics generalizes much better than data-driven systems. And they currently don't take in observations directly. You need a sort of step to do that. So there's research to kind of make this an end-to-end, going from weather observations to forecast. But right now you have to assimilate those observations, basically get this initial map before you can apply them. So this is a case where we have a lot of data, which is similar to what we saw in seismology. What my group is doing is kind of on the smaller data end of the spectrum. So we're interested in emulators for climate. Weather happens every day. Climate is just happening like once. We have sort of n=1 climate. So we have to use these models, and we have to use expensive models as our data. So we're interested in building an emulator for continental scale ice sheet models. These are models that are used to answer the question of how much will the Antarctic and Greenland ice sheets contribute to future sea level rise. We're looking at the end of the century, so the year 2100, so not too far in the future, but sort of the future timeline that's relevant for us as human decision makers. And so for this particular case, we're building an emulator for an ensemble of models called ISMIP6. ISMIP6 stands for the Ice Sheet Model Intercomparison Project. For Antarctica, that's a set of 21 different models that are developed by 13 different modeling groups. And what these groups did is they basically were running a set of shared experiments that they all sort of agreed to run their models on the same experiments. Those experiments take in the outputs of other ocean atmosphere models and the predictions that those climate models make about what's going to happen with, say, the temperature under 2 different emission scenarios, and then projecting how that's going to impact the ice sheets and their sort of melting. So there's a number of different experiments that represent sort of the differences among different climate models and climate projections, and then they make their own predictions about how that's going to impact ice sheets. So we get this ensemble of climate simulations. They span 2 different emission scenarios, a worst case scenario and a more optimistic scenario, so we see sort of the full range of projections. And so what we do is we build a machine learning emulator that takes in those same climate forcings that the ice sheet models were taking. So these are projections of sort of how temperature is going to change under these emission scenarios with different ocean atmosphere models. And then we also put in some parameters that represent the differences between the models, their different characteristics. And then we use that to make our projections using our machine learning emulator. So it's approximating what these models are doing. The advantages of using an emulator for this, again, is really that it's fast. We get much faster projections. So an Antarctic ice sheet model might take something like 140,000 CPU hours to run. We can train our emulator in about 80 minutes on a single GPU and make new projections. So kind of run a virtual simulation in less than a second. Of course, it takes a lot of time to put the data sets together, so that's not reflected here. But it allows us to run experiments and sort of explore the input space and run experiments that they didn't have time to do in ISMIP just because of the sort of computational bottleneck. So we can think of it as we have this sort of sparse set of simulations that the ice sheet modelers were able to run, and we can sort of fill in the gaps of missing experiments. And these are preliminary results that my student is currently doing that right now, where we're sort of filling in these kind of intermediate emission scenarios that weren't run in the ISMET models. So they ran these sort of extreme scenarios, and we're able to sort of virtually run the simulations that are in between. And I'm going to skip over that for time. So I just want to kind of bring together both of these applications and kind of with these new machine learning tools, there are a lot of new opportunities for AI in science, and there are a lot of still challenges. So we see that there's rapid progress in these cases like seismology and weather emulators where we have large high quality data sets. And it's especially when they're supported by these kind of data sets that are available, code that's being shared. And I think with the weather emulators, there are some concerns with that there's a lot of progress on that problem because it's being driven by industry because there's a lot of commercial value to it, and that there are some applications that may be left behind if they're not of interest to industry. There's progress, but it happens more slowly in some of these data limited cases, like in the case of our systems emulator, the ice sheet model emulators. In that case, we have much less data to work with, so it takes a lot more time, especially because the data is very fragmented and hard to get. In earthquake monitoring, we see the same thing. I didn't have time to talk about this, but there are other types of different event classes, other types of data, different concerns when it comes to large events, which are rare, so we have less data for those, where we see progress happening a bit more slowly. But I want to emphasize that domain expertise is really essential for things like problem formulation, data curation, and the evaluation and interpretation of the models. So I think that we can't totally, get rid of the scientists and have things that people with a purely machine learning background. We really need the machine learning and the scientist domain experts to be working together. And I just briefly want to have just one slide on kind of generative AI, since I promised that I would mention that. So this is just my opinion as someone who's an educator of future scientists and someone who's mentoring research students. I don't do research on this particular topic. But my thoughts on this are that we really need to focus on teaching students the fundamental skills and knowledge, both in their domain and in research skills, and that we should think of generative AI as a tool. And to use it effectively, students really need a solid foundation in their domain and in their sort of research skills. I think currently these tools are too error-prone for research use. That's my sort of take on it. And that's partially because there's a general lack of AI literacy among scientists at all levels, not just trainees, also some of my faculty colleagues. And I saw this when I recently gave a sort of generative AI 101 talk in my department. And there were a lot of sort of basic information about generative AI that was completely new to many of the people attending, like that generative AI can confidently hallucinate. They thought if it sounds confident that means it knew the answer. And I was like, no, it's just trained to sound confident. People like confidence, I guess. That there's a citation problem with generative AI, and that LLMs and search engines are different technology. So these were some sort of misconceptions that a lot of scientists had. So I think generative AI has come out really fast, maybe a little bit too fast, and it's people's sort of knowledge of these tools are not keeping up. So that's my thoughts on that. So I'm happy to take questions. Thank you, everyone, for listening.
Wonderful, thank you. Okay, maybe I will start us off with one question. So you raised this interesting idea that these architectural innovations in some areas are not getting better results. Mm-hmm. And that sort of ties back a little bit with some of the stuff that Gary was saying earlier, that we may not, maybe we don't get scaling laws. Do you have any hypotheses about what's going on in those areas and why data is so valuable, but making models bigger or new, more efficient architectures isn't helping?
Yeah, so I think there are some specifics for these weather forecasting emulators. There are cases where the architecture helps. So for instance, with ForecastNet, which is NVIDIA's model, the first version was a Fourier neural operator, and now they've moved to a spherical Fourier neural operator, which takes into account that the Earth is a globe, because they were previously getting sort of the values blowing up near the poles, because they weren't quite, the geometry wasn't represented, right? That's why you see GraphCast is a graph neural network, which can capture the sort of shape. So there are things like that once you capture kind of the key essential properties. I think all of the models they're using, what's key about them is they're sort of big enough that they can ingest the size of data sets that we're talking about. But the specifics of, whether it's a graph neural network or a, neural operator doesn't seem to make that much of a difference. As long as it gets this issue with the poles, right? The spherical geometry seems to be one that's key. So I think in a lot of cases it is kind of the data that's the bottleneck. Assuming that you have a model that's just big enough to ingest it and has some there might be key properties like the fact that the Earth is a sphere that needs to be there. But besides that, it does seem like Like the same with the seismology, there's all these different, there's a transformer, there's one-dimensional convolutional neural networks. The performance is not that different. I think maybe the transformer model might do slightly better, but just with a simple 1D convolutional neural network, you get pretty good results. So it really seems to be, if they're trained on the same data, you often get really similar performance.
Thanks. That was a fascinating talk. Just a quick question on the role of industry. Could you say a little bit more about that? I'm imagining for risk assessment, maybe insurers, financial companies. Are there other application areas?
Well, I guess my concern with the role of industry is just that there are so many different problems in the earth sciences. Like I had this kind of just the list of topics that I showed up here. Some of these, like, I mean, with natural hazards like earthquakes, there's, the insurance industry is interested. With things like weather forecasting, there's a range of different applications. I've seen with remote sensing, there's been a lot of progress in applications related to agriculture, because again, that's sort of something that you could see a business application. But there's other, things that are maybe have less immediate sort of commercial value. And so my concern is that those things might sort of fall behind. The same with small data applications. Like with weather forecasting, you can get, once you have this, realize that you have this big training data set in this ERA 5 reanalysis data, there's a kind of push to like train big models on that. But there are a lot of problems where it takes, like our ice sheet emulators, that took my student all summer to just like get all the data like put together in sort of a standard format and sort of wrangle it to be able to actually work with it. And so those kind of things where there's smaller data, where it requires domain knowledge, I don't know that industry is going to make the investment. I think for the weather forecasting, a lot of times they're interested in like putting these tools out and then sort of leaving it to the scientists to figure out, like to validate them in a lot of cases. So there's sort of just these different interests. And my concern is that we see a lot more progress on things that are not always the fundamental science, but the things that have kind of immediate commercial applications, which is not all of science, right? Like there's a lot of basic science.
Great talk. I enjoyed it. Simulation has always been the domain of HPC, special purpose supercomputers.
Mm-hmm.
Has that changed now with AI? Because it didn't look like you were running this on dedicated supercomputers.
No, so we're training this on just like we're using our local university cluster just because it has a GPU, but you could run it on like a workstation. So to train the models, you can use pretty modest hardware.
So is that a major change? I mean, you don't need to spend
well, you still need to we still need the modelers to run their simulations because we need the data. And so one of the sort of the slide that I skipped is actually saying that we need more, we wrote this sort of paper that's in revisions where one of the things that we say is that we need the people who are running these simulations and the people who are designing the emulators to sort of work together so we can have this sort of feedback loop where maybe there are certain simulations that would lead to bigger improvements in the emulator performance and they could run those and then to get sort of like working together towards answering the scientific questions that are most important to all of us, as opposed to kind of right now the HPC, the people making the models and the people designing the emulators, like we talk to each other because we have to understand, the data that we're getting, but they're not like asking us what simulations to run or what would be helpful for us, right? So there isn't this kind of current feedback loop. So I think some of these things will change. I mentioned.
So change for the better, meaning less reliance on supercomputers?
Well, there would be less reliance for some of the types of experiments that we could do with emulators. So I think that we're not going to get rid of the simulations because we need those as the data. The emulator is just sort of a way to interact with and sort of probe these simulators in a way that you can't if you have to wait, 140 hours to get one new data point. So it's just sort of a different way of thinking about how to use the simulations. We have the simulations, we need them as data, but then we can build the emulators that are this kind of fast approximate version of them that we can then sort of play with or query or ask different questions. So it's not really, we're not trying to replace the simulations at all. One place where we also see interaction between the two is with these kind of hybrid models where they're sort of embedding machine learning like into the HPC simulations. And that's sort of a challenge because they have to get the machine learning to talk to the simulations, which are often written in Fortran. So there's been a bunch of, in these papers that are doing this, the technical challenge is often how do we get the Fortran climate model to talk to the Python machine learning model. But that's another place where we see an intersection as well. But we're not trying to replace simulations. And and still like being able to run those faster, better numerical methods and all that, like that's HPC innovations are still going to be helpful, because the amount of speed up we're seeing with this is like it's orders of magnitude. And so it's just, they might be able to get some improvement on the HPC innovation side, but the emulators are just a new tool to, yeah.
Hey, very cool. I'm curious about, like, you got a whole bunch of data, and you could have some naive model to interpret between like a linear interpolation between them, or some nearest neighbors or something. How often does one of the machine learning models, pick up some interesting behavior that's not like just an aggregate of the data? Some other weird behaviors in the intermediate periods.
Yeah, that's a good question. So I haven't really looked into that as much. There's a lot of work trying to sort of on validating these models. So for ours, our validation is often trying to look and see if like if it's using the right variables, if for instance changing certain ice sheet model characteristics has the impact that we would expect. Things like we would expect the climate forcings to be like the most important variables, and certain like ice sheet model characteristics having more of an impact, and these sort of things. I know there's a lot of work also validating the weather forecasting emulators. I have seen a few studies, which is a conference last week, where they were trying to like use these to answer scientific questions. They try to look at whether they can extrapolate in different cases. So this is an area of active research. With our particular system, we're just starting to run it on these new scenarios, so I don't know yet. We've mostly been focused on sort of validating the model up until now.
So I'm going to take the prerogative to ask the last question. So, one of the challenges I think when you go to conferences here as well is that people present the amazing successes, right? And you're getting orders of magnitude improvement. But one of the things that we're sort of thinking about in this conference is this question about, well, like, is lots of this area going to be automated, just some of it? And I'm curious if you can think of counterexamples either from your lab or other people in the field where people are like, oh yes, I'm going to put deep learning into this part or this part or this part. And you're like, actually our current models are better than that. Has not been a profitable way to go.
Yeah, that's an interesting question. I think the cases where it's often not helpful is when you have very limited data, but a lot of domain knowledge. Like machine learning is going to be helpful where you have a lot of like very large data sets, but you don't necessarily know like the physics. So in a lot of cases, if you want, like these simulations are going to be more accurate than our emulators, because our emulators are treating those as ground truth. So if you want better simulations, like you're going to have to go to the physics, like improve the physics in those models. Machine learning is not going to fix that. So there's a lot of my colleagues will come to me and they're like, I have 4 data points that I collected in the lab doing all this, had to run all these samples, in the lab, and they're like, can we do machine learning? And it's like, well, in those cases, like your knowledge of the system is going to come in, be much more helpful. I think in seismology, one area where that can be challenging is methods looking at some of the larger events. So there's a sort of area of research in what's called earthquake early warning, which isn't what it sounds like. It's basically like an earthquake is already happening and we're in real time understanding what's happening and then giving people like in real time information about it. And the challenge with that is like there's been attempts to use machine learning for that. I think the results there is quite mixed because we just don't have a lot of examples of earthquakes and we don't have them in any particular location. So in a particular location, you only have a big earthquake, once every like 50, 100 years, something like that. So you're not going to have a lot of examples to learn from in those cases. And so those are cases where models are going to be maybe more helpful than machine learning. People are trying to use machine learning. I just haven't been like seen anything that's like really impressed me for that particular application. Although there are some systems that do work that have a little bit of like machine learning in it in kind of a smaller scale, but not like something that requires large numbers of examples because we just don't have those for like a lot of the natural hazards of these extreme events. So
wonderful. Thank you very much.